Okay, that last video was a lot to take in, and this one's going to be equally cumbersome. But the bottom line is we need to learn how to write what are called electron configurations. And I'm going to kind of gloss over these first things, even though Pauli exclusion principle, the off-ball principle, and Hoon's rule are quite important because they tell us how to write electron configurations. We're going to kind of gloss through the first portion of this and skip down to those general rules, and then we're going to backtrack. Okay, so you can see here that she's explaining that hydrogen is super simple. It just has the one electron, so you can use it sort of as a baseline because in its ground state it resides in that first energy level, n equals 1. But when you have elements that have more than one electron or many electrons, then things get a little bit more complicated. So you need to learn how to write what's called the ground state electron configuration, and that's what we're going to learn how to do in this section. Okay, you need to know how to go about doing that, and we're going to use this chart kind of as a baseline in which to do so. Come on, chart. This is also in your text, and it's showing you how you can see here how the energy increases. If you kind of imagine this being turned on its side so that your nucleus is way down here someplace, with your protons and neutrons, so it's way back here, and so this would be your first or your closest energy level. So this would be where the electron for hydrogen would reside, and also for helium. And then here has a little bit more energy, and these have equal energy here because these are your 2p's, and then here more energy, and so on and so on and so on. Okay, and this is what are called your orbitals, and notice how the 2p's are all identical. The 3p's are farther out. They are also identical. They're larger than the 2p's. They're just farther out. Okay, these would be representations of where in space an electron could reside, or there's a high probability of an electron orbiting the nucleus. Now, here are your 3 main rules that are going to govern how we're going to write these in a few minutes. The first is the Pauli exclusion principle, which I've already touched on, that says one orbital can only hold at most 2 electrons. And if it has 2 electrons, then their spins must be opposite. So one is going to be spinning clockwise and the other is going to be spinning counterclockwise. That way they can stay as far away from each other in that orbital as possible. Okay? That's what it's saying. Here's an example of a simple electron configuration for hydrogen. And it shows you right here the 1 in front denotes the quantum number, or what energy level that electron is found in. This right here, this is what energy level. Okay, then you have the S that was right there. That's telling you the shape, or that's generated by the energy from the electron, called the angular momentum. That's what it's called, because it is the momentum of the electron and its spin that generates that particular shape. Okay, denoted by the quantum number L. And then how many electrons live in that particular type of orbital. So here is the electron configuration for hydrogen. Helium also has its electrons in the first energy level, also in that s orbital, but it has 2 electrons that reside there. And notice one of them has this up arrow and one has got a down arrow. That's representing that they have opposite spins. The next is the off-ball principle. And the off-ball principle says that electrons are going to enter the lowest energy levels and fill them first. So we have to build from the ground up, in other words. Notice that she says here, each step involves adding 1 proton to the nucleus. So you're adding 1 to the nucleus, a proton, because that's where they belong, is in the nucleus. And then you're going to add 1 electron to these energy levels. But you have to make sure to put it in the proper energy level and in the proper orbital. And they're going to start from the bottom up. Lowest energy levels must be filled before you can put an electron in a higher energy level. And the S's must fill before the P's can fill. The P's must fill before the D's, and so on. All right, and so this is an example of the off-ball principle in action. These boxes would be representative of the orbitals. Now, you could try to draw these boxes, and I have done so many times so that you can get a 3D picture of what an what an atom might look like. But for lithium, it has 3 protons, therefore it also has 3 electrons. And so 2 of those electrons reside in the first energy level in an S-shaped orbital. And so you'd write we'll just use this screen because I have it here. We have carbon, and so notice that it has 6 total electrons. 2 of them live in the first energy level with opposite spins. Then we're going to move to the second energy level into the S-shaped orbital, and 2 electrons reside there also. And then let's notice the third, the last 2 electrons. They don't go to the third energy level because you have p orbitals. Notice how they fill them. That's Hund's rule. Hund's rule says that if you have vacant orbitals, in this case we have these vacant p orbitals, that if they can, since electrons have like charges and like charges repel each other, that they're going to fill the individual orbitals until they all are filled with 1 electron, and they're going to have parallel spins that's going to keep them as far away from each other as possible until all have 1, and then they'll start sharing. That's what Hund's rule says. So this would be the electron configuration for carbon. Notice you can always double check yourself. Carbon's atomic number is 6, and you should be able to add up these superscripts up top and get 6. That should work every time with atoms. And then here are some more examples of electron configurations. Notice with the oxygen that now that all 3 of them have, all 3 of the p orbitals have 1 electron in it, now then it's doubled up. This last two p's here have now doubled up because all of them have one electron in the orbital. So now they're going to have to start doubling up. Okay? And so that's how you would go about it. And you continue on and continue on, filling each, adding a proton, adding an electron, adding a proton, adding an electron. And the periodic table is designed in such a way to help out with electron configurations. But let's talk about these general rules. And if we need to go back and re-hit those off-ball principle, Pauli exclusion principle, and Hund's rule, you will be tested over those. Those are fundamental in chemistry. And writing electron configurations are fundamental in chemistry. But let's go over these general rules for writing electron configurations. Here they are. Electrons are going to fill those lowest possible energy levels first. That's the off-ball principle. Each orbital can hold at most 2 electrons, and they're going to have opposite spins. That's the Pauli exclusion principle. Okay? And those electrons are not going to pair up in the same orbital if there are empty orbitals available. In other words, this is going to hold for your p's and your d orbitals only. If there are 3 p orbitals and you have 2 electrons, they're going to one go in one of those p orbitals and another one go in a separate p orbital instead of having both of them in the same p orbital. They're going to have their own room, if you will, if it's possible. Okay, and then this is a really good picture of how you're going to fill your orbitals. This diagram is a good rule of thumb. You may have seen it in high school chemistry. It always fills this way: 1s, then 2s, then 2p, then 3s, then 3p, then 4s, 3d, 4p, 5s, and so on, just down this way. This is exactly how your orbitals will always fill. Notice, please, that the 3p orbitals will fill before the 4s's do. That's because by the time you get here, things are so spread out as far as the atom goes that the 4s, that's just a big ball, remember, it's like a big huge beach ball, can slip in between, and those electrons can make that path, its wave path, in between and slide in that 3p. So that's how you're going to, I would commit this page to memory. I mean, or at least print it out, this one slide right here, so that you can have it near you when you're making your electron configurations. It's very, very helpful. All right, and it asks us right here to write the electron configuration for calcium, and an orbital diagram is just the boxes that it was talking about. So we know that since our atomic number is 20, that calcium has got 20 electrons. So when we go about filling these orbitals, this is, we're going to keep in mind our diagram that we were just talking about, that this is how it's going to fill. Your 1s is going to fill first, and then your 2s, and then your 2p's, and then your 3s, and then your 3p's, and your so on. So when we do this, you would say, okay, I have I have 20 total electrons. So when I'm drawing this, you're going to have to think to yourself, okay, it's going to fill this way. This box would represent my 1s's, and it can fit 2. Then this box here would represent my 2s's, because they're going to fill next. See this diagram, my 1s's, and then my 2s's are going to fill next. What fills next? Your 2p's. That's 3 boxes. How many total can fit there? 6. Remember, I'm trying to get to 20 because the atomic number of calcium is 20. So far I've got 2, 4 plus 6 makes 10. So I still have a ways to go. So there's 1, 2, 3, 4. Then these are going to fill one at a time. 5, 6, 7, 8, 9, 10. I'm only halfway there. So now I'm going to move to the next energy level, which is the 3. And on the third energy level, I have 3 S's, and I also have P's. So there's 2 that are going to reside in that orbital, because that's a 3s. And how many electrons can fit in an s orbital? Only 2. Only 2. And then my p's, I have my p orbital right here. How many electrons can fit in a p orbital? 6 altogether, because there's 3 of them and 2 can go in each one. So here they go. They're going to fill one at a time, one at a time, one at a time. So let's count how many we have here. There's 10 up to here, then there's 12, 14, 16, 18. So far I have 18, so I'm allowed one more box. So 4s2, opposite spins. So my electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. That's the electron configuration for calcium. You would add up your little superscripts up top and make sure they all add to give you 20, and that can help you know that you got it correct. Okay? And then it's always nice to be able to use your periodic table, and you can use the periodic table to help you take shortcuts, because if you can get to the noble gas, that's every atom's goal in life anyway, is to become stable like a noble gas. And let's take calcium, for example. Calcium has 20 electrons. The closest noble gas to number 20 is number 18. So you could have written calcium's, I know this is not this slide, but let's pretend that it is. Calcium which is atomic number 20. The closest noble gas to atomic number 20 on the periodic table is argon, number 18. So we could do away with all of this business that we just wrote, number 20. We could do away with 18 of those, the 1s2, the 2s2, all that mess, all the way to 2p6, which is, 3p6, which is argon. And we could just put brackets like so and say argon, the noble gas argon. And then what came after that was 4s2. This is a shorthand way to write calcium. Now don't get too comfortable with that, because you're going to have to do it the longhand way first. Okay? Alright, and there's also, look at your periodic table, and in your periodic table is really, really going to help you with these, because your periodic table is designed in such a way that it shows you on the side the energy levels for easy viewing. This picture on this one, it shows you right here. This one is actually giving you all of the electron configurations for you, which is cheating big time, I think. But it gives you the core would be helium, and then this gives you the energy level right here, energy level 2, energy level 3, and so on. Okay, but also after that you would put neon 3s1, that's the electron configuration for sodium. Neon 3s2, that's magnesium. But if you were doing it the old-fashioned way and you wanted, say, beryllium or whatever, or maybe you wanted aluminum or any of the elements, then these numbers on the side over here would certainly help you, because they're going to show you that here's atomic number 1. Oh, did I? Come on. This is being very slow this evening. This is, if you wanted to do, let's say we wanted to do nitrogen, and it shows you the shorthand. It shows you that your core would be helium is your core, and then you would just write, since we're on this row now, the second energy level, there's your 2 right there. And look at this. Your periodic table is designed in such a way, this block right here is your S's. All of these are in your S's. So S, and there's 1, 2. And now we're going to move right across the periodic table. We're still in the second row. So there's 2, P, 1, 2, 3. So your periodic table is designed the way it's designed on purpose. Okay? Notice this block down here. Well, I'm going to take this away. I'm going to do it in this green highlight right here. This block right here are your D's. Those are your D orbitals. And notice that they're dropped down from the others. And that helps me to remember when I get to my D's, I need to drop back 1. So this one is not actually a 4D, it's actually a 3D. And this is 3D2, 3D3, 3D4, and so on. So when you're writing those, they belong with the 3rd energy level and not the 4th energy level. Okay? So that's why scandium is a 3D1 and a 4S2, because the 4S2 is from calcium, and then scandium is 3D1. So that's why it looks like that. So scandium would be a core of argon. So I put argon core, and then it's 4S2, 3D1. But 3 comes before 4, so you actually write the 3 first. Okay? So it kind of looks funny. All right. I hope that helps. We're going to work on those even more, because the next chapter is like that as well. And then this next slide talks about the lanthanide and actinide series. But I think that we're going to call that a day, and I'm going to give you some time to practice on that. Chapter 7 also is talking about electron configurations and how they're used in bonding, and the different types of bonds that S orbitals and P orbitals, when they join together, they form clouds, bigger clouds, and they form bonds, and that's what it deals with. And then this is talking about some anomalies, and you can see on here that these anomalies occur that, like chromium here, even though it should have a core of argon and 4s2 3d4, it's just been found experimentally that having a half-filled subshells like this is just way more stable than having a full S orbital and only 4 Ds instead of 5 D orbitals filled, with 1 electron each, having all of them each having 1 instead of 4 of them having 1 is much more stable. And so chromium is different in its boxes, that's all. So that's not as big an issue at this point. You need to learn how to write electron configurations in the first place. Okay. So I'm gonna let you practice on these, give you several to actually practice, and then hopefully we'll communicate more. But that ends chapter 6, and then we're going to work on chapter 7. You have a good evening.